So this is the Unit 1 review, and we'll start with the first standard 1.1. So the first question in the standard asks, what is the position of Addison relative to Belmont? Addison's here and Belmont is there. And so relative, it is whatever distance is between them, which is 1 kilometer, and specifically 1 kilometer north of Belmont. Then the next question asks, what is the position of Addison relative to Fullerton? And so here we're looking at Fullerton. Addison is again north, but this time we're going to have to add both of those distances. So it is 2.8 kilometers north. The next question asks, what is the position of Addison relative to Sheridan? And in this case, Addison is south of Sheridan by 0.8 kilometers. And then number 4, it starts to ask us about more complex trips. So it's not just the location of one thing in relation to another one. This rider goes from Fullerton to Addison and then to Belmont. And so when we're looking for the distance, what we need to do is take each leg of this trip, take the absolute value of it and add it up for a total of 3.8 kilometers. But the displacement only takes into account their final position and their initial position. And so we can look at their trip up to Addison and back down to Belmont. Since one is positive or one is north and one is south, then one is positive and one is negative when we are calculating this displacement. And so really they cancel one another out, and the displacement is just the change in position from where they started to where they ended, which is like from Fullerton to Belmont, as if they had never gone to Addison. Looking at these individual displacements, though, we can see that if we took the absolute value of each, that's how we would have gotten the distance calculation in part A. 5 asks about a rider going from Belmont to Addison and then from Addison to Sheridan. And so if we look back at the map real quick, we'll see that these trips are both to the north. They don't do any backtracking. And therefore, you'll see that their distance and their displacement are the same magnitude, but the displacement has a direction because displacements always have directions. But since there's no backtracking, the size of the numbers is exactly the same. And then in number 6, we have someone who leaves from Addison. They go to Fullerton and then back to Addison. And so here we've got quite a bit of distance because they're going 2.8 each leg of their trip. And so their total distance is 5.6. But since they end up in the same spot that they started, their displacement is 0 kilometers. For our second standard, we're thinking about speed and average velocity. So here we have a horse that's going to go 38 meters away from their trainer and then 19 meters back in a specific amount of time, 9 seconds. And so for the average speed, we're going to use this equation, which is distance divided by time. We can then calculate the distance by taking the absolute value of each part of the trip, so 38 meters to the right and 19 meters. It doesn't matter which direction that 19 meters is. And then we're going to divide that by the total time it took. So it took them 9 seconds on the way there and 1.8 seconds on the way back. And if we calculate this quotient, we get 5.28 meters per second. In part B, it asks what is the average velocity. And so for the average velocity, we're looking at just the displacement, so where they started and where they ended. In this case, the displacement is just 19 meters to the right, but the total time is the same as in part A. And so when we divide this, we get positive 1.76 meters per second, or 1.76 meters per second to the right, because to the right is what this positive sign is communicating. And then part C asks us to compare these two values. And because they rely on different numerators, they then have different sizes. And because the numerator in part B has a direction, then the answer has a direction, whereas in part A, the numerator and the answer both are directionless. And for number 8, we have a race car that travels at a specific speed, and they tell us how much time they spend traveling the speed, and they ask us how far it goes. And so we'll use this equation to solve for velocity, to solve for how far it traveled. Given the velocity, we'll plug that in on the left side and the time on the right, and then we'll multiply both sides by 12.5 to get an answer of 1,187.5. In 1.3, we have 2 graphs and some questions about both of those graphs. So the first question asks us to just look at figure 1. It asks us which person started left of the origin. And remember, on a position time graph, this is the origin, and anything down here is left of the origin. So we're looking for objects that started left of the origin or had a y-intercept that was a negative position. So the items that start with a negative y-intercept on this graph are C and D. For part B, we've got which person was moving to the left initially. And so moving to the left on a position time graph is shown with a negative slope. And so negative slopes are shown for person A and person B. In question C, it says which person was moving the slowest. And so for slowest, we're looking for the least steep slope. So it doesn't matter if it's a positive slope or a negative slope. We just know that a very steep slope in either direction is fast. And so we're looking for something as close to horizontal as possible. And the one that's closest to horizontal is C, which is the answer to part C. Then for the next 3, we're looking at figure 2. It asks us which time is the object moving to the left. And so leftward motion on a velocity time graph is anything that is a negative velocity. So in this case, it is G. Part E asks us what direction was the object moving initially. And so initially we're looking at E. And since E is in the positive velocity range, positive velocity means right, a rightward velocity. And then part F says, using figure 2, when was the object moving the fastest? And fast in a velocity time graph is how far away from the time axis you are. So anything up here is moving to the right. Anything moving down here is to the left. But then if we're talking about speed, then really the slowest speed that someone could go is moving 0 meters per second right in the middle. And then up here would be fast, and down here would be fast. They would just be in different directions. And so we're looking for which segment is farthest away from the time axis. And the one that's farthest away is segment F, which is the answer to part F. For the next standard, we have 2 questions. Number 10 asks us to look at a position time graph and find the velocity of the final segment, which is from 5 seconds to 10 seconds. And so in order to find that velocity, we know that the velocity on a position time graph is shown with the slope. So we can calculate the slope with the final position minus the initial position divided by the final time minus the initial time. And if we divide this, we get a slope of negative 2.8 or 2.8 meters per second to the left. For part B, it asks us what the hippo's velocity was at 4 seconds. And so at 4 seconds, we're looking at right here. But it's impossible to find the slope at one point. And so what we need to do is we need to find the slope of the line that goes through that time of 4 seconds. And so instead, we're going to be looking at the slope again. But this time, we're looking at the slope from 3 seconds to 5 seconds, because that includes 4 seconds. And we can find that slope to be a positive 2 meters per second. That positive communicates that this velocity is to the right. Number 11 is about a falcon. It's a velocity time graph instead of a position time graph. And in order to find the displacement on a velocity time graph, we can find the total area of each chunk and add them up. So for the first 4 seconds, the area is positive 8 meters. For the next 2 seconds, it's a negative 4 meters. And for the last 4 seconds, it's a negative 16 meters. All added up, that is a total of negative 12 meters, or 12 meters to the left. And then when we're looking for the distance in part B, we're going to take the absolute value of each one of those sections and then find that sum. And so the sum of the absolute values of each individual displacement is 28 meters total for the distance. You'll see that in the second and third part of the motion, that by taking the absolute value, it disregards that we're moving to the left, and so therefore it doesn't decrease our distance like our displacement sometimes does with a negative motion. And for the last standard, here we have a position time graph, and we're trying to translate it into a velocity time graph and a written description. In order to make a velocity time graph, we need to find the slope on this graph. So the first slope is right here, and to find that slope, we can take the final minus the initial for both position and time. And we see that it's negative 1 for those first 4 seconds, and so that gives us this line that starts at a velocity of negative 1 and starts at 0 seconds to 4 seconds. That's the first chunk of the velocity time graph. Then we have the next chunk, because this is a different slope than the first 4 seconds, and so for this slope, we need to do another calculation, which gets us a positive 4 meters per second. And so we'll go to positive 4 at velocity on the velocity time graph, but we're going to start this at 4 seconds and then go to 6 seconds. So that's our second segment of the velocity time graph. And then the third segment on the position time graph is horizontal. And so finding the slope of this section, mathematically, it is 0 meters per second. And so that will be right on the time axis of our velocity time graph. So our velocity time graph is done. Now, in order to describe this motion, we'll start by stating the original position, which is 2 meters right of the origin. We know that it's right because it is a positive 2 meters. If we started down here, that would be 2 meters left of the origin. We'll then describe the first chunk of motion, which is that green line. It's moving to the left because it has a negative slope, and it's at a constant velocity of 1 meters per second. That's what we found in our green calculation, and the time duration is for 4 seconds. Our next section of motion, shown in blue, is moving to the right because it's a positive slope. It's 4 meters per second that we found in our blue calculation over here. And the duration is for 2 seconds. And then in the last 4 seconds, it stands still. So you don't need a direction for standing still. In our second example, we're given a velocity time graph. And so in order to put this onto a position time graph, really we don't know what the starting location is, and so we can start anywhere. We decided to start at a position of 0 at the origin, and so for the first 4 seconds, because it's not moving, because its velocity is 0, then we're going to show on the position time graph that for the first 4 seconds, the position continues to be at the origin. But then after that, we're going to look at this rectangle right here and find its area. And so the area of this rectangle is its base of 3 times its height of negative 2, which is negative 6. And so then we need to go negative 6 from this position of 0 in the same time duration of 3 seconds. And so what that gets us is 3 seconds later, 1, 2, 3, we need to be 6 meters left of 0. And so in this case, 6 meters left of 0 is negative 6. And so then we'll see that this is the line for our second section of motion. We can repeat the same process here And here we've got a rectangle that is 3 by 3. So we can find that the displacement for the last 3 seconds is 9 meters to the right. And so then from the position that we left off at down here, 9 meters right of that would be a positive 3. And we have to do that in 3 seconds, which gets us this endpoint in that line. To describe this motion, we can't really talk about the initial position because we just picked it randomly. And so we'll go right to the first type of motion that is exhibited, which is not moving at all for the first 4 seconds. Then it's moving left at a constant 2 meters per second. And again, we saw this 2 meters per second here. That's how we can tell its velocity. And the duration of 3 seconds is there. And then our last piece of motion is 3 meters per second to the right. And that's also for 3 seconds. And in our last problem, here we've got a written description, and we're going to create both of the graphs. And so I would actually encourage you to start by trying to make the velocity time graph, because this is just given to us in velocities with directions and time durations. So it starts at a certain location that's not shown in the velocity time graph, but then it moves right at 2 meters per second for 4 seconds. And so we can find 2 meters per second since we're right at the start of the time, and then we're going to continue that same velocity until we reach 4 seconds right here. Then the object moves to the left, so we're going to have a negative velocity, and it does so at 1 meter per second, which this is where negative 1 meter per second is. And it's going to be for 3 seconds. So we're starting at 4, going to 5, 6, 7 seconds. And so we'll see our first 2 sections of our velocity time graph. And then for the last 3 seconds, it stands still, which is a velocity of 0. Now we're in a pretty similar situation as we were in the last one. We can start our position at 4 meters left, which is negative 4 down here. And then what we should do is figure out what the area is of this rectangle in the first part of the motion. And so that area is positive 8. And so we started at negative 4. And after 4 seconds, because that's the base of this rectangle, after 4 seconds, we need to be 8 meters right of where we began. And so to figure out where we have to end up, we can take our initial position and add on that displacement. And so we'll end up at positive 4 meters 4 seconds later, which gives us our first section of our position time graph. Then we can do the same thing with the second section of motion, which is 3 seconds for the base and negative 1 for the height. That gives us a displacement of negative 3 meters. And so we know that after 3 seconds, we need to be 3 meters left of where we left off. And this is where we left off up here, which is at 4 meters. And so to figure out where we're going to end up, we can add that initial position to that displacement and see that we have to end up at positive 1 at a time of 7 seconds. And then for standing still, we're just going to have a horizontal line on our position time graph, because the position that it was at 7 seconds, which was positive 1 meters, is going to continue to be the position until 10 seconds. Thank you very much for watching.